Ostowski. I work in technical support department of OriginLab Corporation. I'll be conducting today's webinar on user-defined fitting functions. As an introduction, I assume that if you're at this webinar, you know a little something about nonlinear curve fitting in Origin. And you maybe at some point have found that we don't have a fitting function you need. And so therefore you need to create one yourself. So this webinar, it's really meant to be an I'm not going to go into huge depth, but I'm going to show you how to create a user-defined fitting function using simpler functions. After you watch this webinar, you should be able to be competent in doing the steps that are necessary to create a user-defined fitting function. I'm going to start with the simplest way to do it with our Simple Fit app. And then I'm going to introduce the various tools associated with fitting and defining fitting functions. And I'm going to create 1, 2, 3 fitting functions, no 4 of them, including one that's a peak fitting function and one that's a fitting with integration. Then I'll show you how you can share your fitting functions with others. And finally, I'll introduce some of our apps related to creating fitting functions. A little bit later in the webinar, I'm going to pause for a couple of minutes so we can have a poll that we would like you to take a minute to fill out, but that will be a little bit later in the webinar. Okay, let's get started. And I told you the first thing I would do was show you the simplest way to create a user-defined fitting function, and that is with our Simple Fit app, which ships with Origin. Now here I have a graph, and it's actually a graph that's embedded into a workbook. It's become one unit, and I want to activate this graph because this particular app works from graphs. And what I'm going to do is I am going to fit this data. This is a Gaussian kind of peak shape, and I'm going to fit this to this very simple Gaussian. Let me just copy this because sometimes it's easier for me. You may observe during the webinar that I have notes for myself, but these are not just notes for myself. They're going to be notes that are going to be available when we share the project. So you may see me copying, some of the fitting functions, the more advanced equations. I'll just copy them rather than manually type them in to save time. So I want to fit this data with this function, and it's Gaussian. And according to the original function, we have an amplitude variable, we have a B variable, which is our peak center, and we have a C variable, which is the peak width. So let's start our app, and I will show you how this works. I come to my app center. It's along the right side of Origin, and I click on Simple Fit. A dialog opens, and sometimes you may have to select between linear, polynomial, and nonlinear. So I selected the fitting functions we create today aren't necessarily nonlinear curve fitting functions. You can't define your own linear or polynomial functions. So the idea here in this app is I type in my equation into this box. Now I said I copied it a minute ago, and let me just paste it in so you can see. And what I've had to do is I've had to take this equation and go from the form that we see it displayed on the graph into a form that is like computer code. It is an actual equation, and this takes a little bit of practice on your part if you're not familiar with it. For example, we have the E here for exponent, but we have in Origin we have to use what's called an exponent function. For our power, we have to use our caret symbol. The caret symbol means to power. So we have an exponent function, and the contents are wrapped in parentheses. So we have this function form. All we have to do is tab out of this control box, and Origin is going to parse that function and extract the parameters. That A parameter, which is this A parameter, it's capital A. I converted the parameters from A, B, and C to more meaningful ones, including capital A for amplitude, XC for the peak center, the X center, and W for the width. So once I've done this, we can see that there's a line, our fit line on this graph, but it doesn't really have any meaning right now. We really can't do much with it because we have to provide some initial values for these parameters, something for origin to start with. So let's look at this and see what we want to do. For our amplitude, maybe we can start with 80. So I'll come down here and I'll replace that one with 80. For our peak center, our XC, it's somewhere, let's say it's about 22 or 23. And finally, our width, I'm going to guess our width is about, let's say it's about 5. Let's see what those look like. Well, they don't have to be perfect. We're just putting initial parameters to sort of guide origin in the right direction. So we've defined a function. We've given it some initial parameters in this particular app. Now I'm going to click the fit button. And when I do that, Origin ran the fit very quickly. It said the fit did converge. We see the fitted line on the graph, and we click report. And Origin will generate a report for us. We don't have the recalculate. If you're used to using our more robust nonlinear curve fitter, it supports recalculation. This simple app does not support recalculation. It is really meant to teach. It is a learning tool to learn how to define your own functions and learn how the fitting process works. But let's look at the more robust tools now. There are a number of tools associated with defining your own user-defined fit function. Of course, if you've done any fitting in Origin, you are familiar with our nonlinear curve fitter. Let me just open that up for a minute to show you. You are probably already familiar with the idea of selecting a category and a function and doing the fitting, this process. And we'll go ahead and go to our report sheet. But not only do we have the nonlinear curve fitter, we have the peak analyzer. That's another area where fitting is used and where user-defined fitting functions can be used in Origin. I won't open it up right now. We'll do that a little bit later when we define a peak fitting function. The tool we're going to use more often is one, and we'll learn about that in just a minute, called the fitting function builder. And the last tool is our fitting function organizer. This is a dialogue. It's like a library dialogue that lets us look through our fitting functions in Origin. On the left side, we have a folder structure. Our fitting functions in Origin are grouped into folders, categories, and we can expand the categories. And as we look through, if we select a function at the bottom of the dialog, we can see its equation. We can see a sample curve, maybe some hints about it if there are any. And we can look through. This can help us if we need to find a fitting function in Origin. This can help us maybe find the applicable fitting function for our needs, such as these exponential association functions. As well, this tool lets us organize our fitting functions. We can move them around. We can move to different categories if we want. I won't actually do that with the built-in fitting function, but we can move categories. We can start a new function from here or create a new category. This is, so as the dialog title says, this is really for organizing your fitting functions. And we may need to revisit this a little bit later. So those are our tools. Now let's start with the very basic user-defined fitting function. This is where we're going to learn about our fitting function builder. Again, I'm going to use the same function I just used for the Simple Fit app, but we're going to define our actual user-defined fitting function. And we do that by going to our Tools menu. By the way, I'm using the latest release version of Origin 2020B. Most of the features here are available in older versions of Origin. Some of them may not be available in very old versions, but for at least the last 3 or 4 versions, everything I show you here today should be in it. So let's go to our Tools menu, and I'm going to go slowly today on this so you can see. From our Tools menu, we choose Fitting Function Builder. And we get a dialog. It is a multi-page tool. Some people call it a wizard. That's an older term. The idea is we use this tool to go step by step and create a fitting function. We are starting out with a new function. So I select that and I click next. In our introductory page, we have to choose a category and give the function a name. Usually it's best to put your fitting function in the user-defined category. If you do not see that on the list, it's on my list, but if you don't see that, you can define a new category this way and call it user space defined. So that is where our function is going to go, and I'm going to give it a name. We're going to call this a simple Gaussian, because it's the same. We're going to use the same function we used for the Simple Fit app. Now, this is an explicit function. It's not implicit. Implicit functions are for things like circles and ellipses. We're not going to be fitting that type of data, so it's an explicit function model. And we have to define what type of function are we going to have. You can define functions different ways. Your equations in Origin. The simplest one is called an expression. That's where you just put in an equation that's been converted to code Origin knows. It's the easiest one. It's very fast. An equations type function type allows you to have multiple lines. For example, define some variables that then you use in your function. We have Origin C fitting functions. Origin C is a built-in programming language in Origin. It's very powerful. You can do things like add control structures to your fitting function. We'll look at an example of that with a peak function. Origin C fitting functions, however, tend to be slower than expression or equation type fitting functions. We also have LabTalk script fitting functions. These are outdated pretty much, and they're older, they're outdated, and they're very slow. They still have a purpose. We won't be doing one of these today. Finally, we have external DLL-based fitting functions. These are for power users. These are for people that are willing to use something like Microsoft Visual Studio and C or C++ to define a fitting function to create a DLL. They are very powerful and they are very fast, but it requires a lot of knowledge that may be out of the scope of most Origin users. For this function, we're going to use this simple expression type. I will click next. And now we need to define in this one, what are our independent and our dependent variables and our parameters. Almost all the time, your independent variable, we're going to use X, and our dependent variable, we're going to use Y. Sometimes it's different, but for today, we're going to keep those as X and Y. And our fitting function is going to use the same parameters I used in the Simple Fit app. I'm converting that ABC to capital A, XC, and W. So I need to list them under parameters. And Origin has already given me the A parameter. It just defaulted to decide to give me the A. So I'm going to put a comma here. Then for that peak center, that X center, I'll use XC, comma, W. So I've defined my parameters. In my next example, we'll do derived parameters and constants. We don't need to worry about them now. And this is not a peak function. We'll do a peak function later. I will click the next button. Now we need to define our function body, and if we want to give our parameters some initial value, I'll show you a little trick. If you've got your, for example, your equation somewhere else and you just want to copy and paste it like I did, in this dialog, you can click the minimize button. Origin will give us a little prompt, and when we say, okay, the dialog rolls up. It kind of defocuses, allowing us to move our mouse over and to select our actual function. It's the same one I used for the Simple Fit app. Then I can come back to my dialog and click the minimize button to bring the dialog back. So for the expressions, we don't need to manually put y equals. We already have a y equals here. In this case, I'm just going to leave these initial parameters as what Origin chose as 1. If we want to see that our function works, we can click on the quick check button with And Origin, if the function works properly, should return a value for y based on the value for x. Now, there are other steps in this tool, but for this simplest example, we don't need to go through them. So I will click Finish. And now we're ready to use our fitting function. We'll fit off this graph, so let me activate the graph. I will go to Analysis, Fitting, Nonlinear Curve Fit, and I will open the dialog. We created a user-defined fitting function, so let's go to the user-defined category, and we'll select our function, Simple Gaussian. And when I do that, I see that Origin has initialized the parameters, and they're not any good. I did not give them sensible initial values when I defined a function. But as you may know, in our NL fit, our actual fitter, we can give them initial values here. So let's do the same values we did with the simple fit app, 80 for amplitude, maybe 23 for the peak center, and maybe 5 for the width. And when I initialize them here, we can click the Fit Until Converged button, and we can see the Origin it's used our our user-defined fitting function to do the fit. So that's a very simple user-defined fitting function using our fitting function builder and our nonlinear curve fitter. Let's look at a more complex fitting function, one that has derived parameters and uses a constant. This is our function. I apologize for the blurriness. I copied and pasted it from our website. I didn't have time to improve it. It's an exponential function. We've got a constant in here, 2.303. It appears a couple times. We have a number of parameters. Let's use our fitting function builder to create a fitting function. And before I open it, I'm just going to copy my fitting function real quick so I don't have to type all that in. So from the Tools menu, and let me get there, I'm going to go to Fitting Function Builder. Again, I'm going to create a new function. Again, I want to put it in the user-defined category, and if that category doesn't exist, we just create it. And let me just give this a name. I'm not sure. Let's see, my function 1. I'll just give it a simple name. You may want to give it a better name. You may want to give it a description. A description can be very useful. Again, this is explicit. This is an explicit function because this is concentration curve data. Again, I'm going to use an expression because it's the simplest thing and it's fast. So I now click Next. Again, we have to define our independent and our dependent variables. So I'm going to keep those as X, Y. For our parameters, let's look at let me minimize that. I'm going to make that prompt not show up again. Let's look at our function. Our parameters, we have an A, we have a K, we have a KM, we have a C, we have a C0. So let's go ahead and enter those in our list, separate them by a comma, A, KM, K, C, and C0. We're going to have a derived parameter. We're going to call it A0. A derived parameter is a parameter that is calculated after fitting using values from the calculated parameters. It's another way to provide a parameter for the result. So we have a derived parameter. We're going to define it later, but I'm going to call it A0. And we need a constant for that 2.303. I'm going to call that constant. I just decided to call it R0. It doesn't really matter what you call it as long as it's something that means something to you. And with those defined, I'll click Next. And now we need to place our function. And again, I was lazy and I copied it so we can just paste it here. And this time, rather than accept these default initial values Origin gives us, let's go ahead, based on some a priori knowledge of some initial values that are close to what the real values would be. And I've worked with this function before, so I know some of them. I happen to know the good initial value for A is 325. For Kn is 10. K is 1. C is 0. C is going to be 2. And C0 is going to be 0.1. So I've given it initial parameter values. We also have a constant, that R0. The constant, we have a parameters tab here. We also have a constants tab now. So we need to give R0 a value, and that's going to be that 2.303 value. And while I'm here, I want to stress something. In many countries, you use a comma for a decimal separator rather than a period. If you use Origin with that setting, you may be tempted in these dialogues where there's a decimal place to use a comma. In cases like this, and in your formulas, if you have a decimal place, please use a period, use a dot, don't use a comma. The comma may not work correctly. So go ahead and stick with that dot when you're using these when you're using these numbers here or your function bodies. We can do a quick check just to make sure our function works, and we did get a value. This time, instead of stopping here, we're going to move on. And we move on. This is another place to define initial values. We're not going to use this page here. We'll use this when we do our peak fitting function. So I'll skip to next. We get to a page that lets us define bounds for our fitting function. Bounds are a way for Origin to limit the upper and lower values for parameters. You can either define them here in your fitting function, or you can define them later when you're doing the actual fitting. For our example today, we won't use any bounds, nor will we use our general linear constraints. We're going to try to keep things simple. I will click the next button to look at our next page. Here is where we have to define what our derived parameter is. If you remember what I explained a derived parameter, I said we had one A0. So we need to actually do our equation here and define A0 as minus our calculated A parameter times exp, and that's the exponent function, the exponent of km, times, we use asterisks for times. If you've done programming, any even basic programming, you understand the asterisk is used for the time symbol. And we're just going to say 1e to the minus 4, that value. So we've defined what our derived parameter is going to be calculated as. Next, this is our final page. This is for defining a LabTalk script before we do the fitting and after the fitting. This is somewhat older. It's very rarely used anymore. This was used more before we had the system for defining derived parameters. This is where people in the old days used to define parameters. We just keep this available for perhaps someone has an older fitting function they're editing. This is why this is available. And now we can click Finish. So we've defined our second user-defined fitting function. Let's take a look at it in action. We'll go to Analysis, Fitting, Nonlinear Curve Fit, and open the dialog. In our function selection, of course, we have user-defined. That's where I put the function, and I called it my function number 1. And when I did that, let's see about our initial parameters. We have our initial parameters. Let's see what happens when we do our actual fitting. Okay. We got a fit, but we got a warning. It did not converge. A mutual dependency exists. And it suggests that we maybe have over-parameterized our function. And one thing we can do is to fix one of our parameters. So let me reinitialize the parameters. And I'm going to fix this A parameter. In fact, it tells me in my notes here when fitting, fix the A parameter. So I'm going to fix that prior to fitting it. And now when I fit it, I get a good fit, a nice R square, and I can say OK. So that's our second example of a user-defined fitting function. This time we added derived parameter, and a constant. Now let's change gears and look at an origin C based peak function. I have a peak here. It's actually a mixed Gaussian. It's two different Gaussian shapes, sort of a half and half Gaussian. We actually have a similar built-in function called a bi-Gaussian, but we're going to define our own simple function to handle this. And we're going to use origin C. The reason we're going to use origin C is we're going to have a control structure that I'll show you. All right, again, let's go to Tools, Bidding Function Builder. We have a question. Where does the derived parameter from my previous example, A0, get reported? It gets reported in the report sheet. You may see here on our report sheet A0, it did get reported there with the other parameters. Okay, so let's go back to our peak function. Again, we're going to use the same tool, the fitting function builder. We're going to create a new function. And here is where we need to do something different. For normal fitting functions, we want them to go into the user-defined category. For user-defined peak fitting functions, we need a different category, and this is not entirely obvious. We need to go into the PFW category. So try to remember that. If you didn't if you didn't put it in the right category, if you didn't put any of your functions in the right category, you can use that fitting function organizer to move your functions around to whatever category you want. For example, if you are putting the function we are about to define into the user-defined category, and it needs to be in the PFW category, you can move it from the organizer. So we're going to call this function my peak function. It's still going to be an explicit model. I'm not going to do any implicit models today. This time we're going to use an origin C instead of expression. I'll click the next button. Now we define our variables. Our independent's going to stay X. Our dependent's going to stay Y. What do we have for parameters? We have a Y0. Y0 parameter is going to be the baseline. We have an amplitude A parameter. We have a peak center. We've been calling it XC all along. And instead of having one width parameter like you typically see in a peak, we're going to have two different width parameters. We're going to have W1 and W2. We won't have any derived parameters or constants, but, and this is very important, we do have a peak function, so we're going to check that. Oh, by the way, I did not mention that this tool actually has hints along the left side when you go step by step. It offers suggestions and hints and things like that. They're fairly useful if you take the time to read them. So I will click Next, and here's where we define our function. In Origin, it's a little different in Origin C. We can paste our function here, which I will do. But we have to compile it. So what we're going to do is we are going to click on this button here, Open Code Builder. Code Builder is our IDE, our integrated development environment in Origin. This is where you do coding from Origin C, and I'll show you why I did Origin C. I had what is called a control structure. I had an if statement, and my if statement says if the x value, this function gets called, this fitting function gets called for every x value. So it's saying if the current x value is less than the peak center, then you're going to run one function. Otherwise, you're going to run another function. One calculates the width, the W1 param, one calculates the W2 param. So with our code builder open, we need to compile it. And this way we'll look and see if there's an error in my fitting function that the code builder would complain. Let's provide an example. I'm just going to break the if statement by putting a space in. So if I try to compile it, we'll get a complaint here. So let me fix that. Compile again. Our fitting function compiles, which means it works properly. And I will return to this dialog. Now, I can click on the quick check, and it gives me a warning. Please use your peak attribute column to assign attributes. So we need to do this up here. This is our peak. This is only for the peak functions. And we have Y0. Origin figured out it's the offset. We tend to, in origin fitting functions, in our origin world, we usually always set a baseline as Y0. But we have an A, and that's an amplitude. So from the drop down, I'm going to choose the amplitude or area. XC is the peak center or the X center. I will choose it. W1 and W2 are both widths. So I will choose X width for both of them. So this is a requirement to go through and assign peak attributes to a peak function. We could put initial values here, but I'm going to show you another feature of the fitting function builder. Let me click the next button. And here is where this page that I skipped the last time, here's where this page is useful. We make it pretty easy to define initial parameters based on calculations. We have this flyout here where we have all sorts of values Origin can calculate, like the minimum X value or the minimum Y value or the first X, last X, all sorts of ones. X at Y50, Y at X max. So what we want for that Y0, our baseline, is our minimum Y. So let's find that. Y minimum. And it'll put a little piece of code in there Origin uses. For our amplitude, we're going to choose our maximum Y, Y max, and we're going to subtract our minimum Y. So, and I can just actually type this in because the minimum Y would be Y min. Okay. For our peak center, we're going to find our X center on this list. X. Let's find the X center. It's a long list. We're going to choose peak center instead of X center. For width 1, we're going to choose our peak width. That will be the width of this entire peak, but since we have two different widths, we're going to divide that in half. And we're just going to enter the same one, P width, divided by 2 for the other width. So those are our initial parameter calculations. I'll click next. We're not going to do bounds or constraints where we don't have derived parameters and we don't have scripts, so we can choose finish. Okay, with our peak function defined, I will activate our graph and let's fit this peak. Let's go to analysis, peaks and baseline, and open our peak analyzer. All right. One thing to keep in mind is that the defining your own peak fitting function is an Origin Pro only feature because peak fitting is an Origin only Pro feature. Origin Pro only feature, pardon me. So we're going to decide to fit our peaks. I'll click next. We're just going to accept some default values because we're more focused on the function. So we're going to accept the default baseline. We're going to leave these settings default. We're going to let Origin find the peak center. There is only one. Our little symbol there is a block shape. It should be square, but it's a block shape, but that's okay. We can click next, and we'll get to the page where we can get to our fit control. If you've ever used our peak analyzer, this is where you go to manipulate parameters and choose a fitting function. Let me make the dialog a little, resize it a little bit. And here is our drop down for our function. And when I look, Origin has scanned that PFW folder for my user defined fitting function, and it's at the bottom. It's marked off as a user function. So I select it. And when I do, we can see our initial parameters, that those codes we entered, those p width, etc., they helped Origin calculate an initial values. So now all we have to do is fit until converged, and we can see that our fitting function has worked well. We've got a great R-square COD. So I just say okay, finish up, let Origin do its thing. We'll go to our report, and it's just a typical peak fitting report. We got to look at the function. Let's look at the notes. We should have the function listed here. It's the model, my peak function. It is a user function. So that's how we do our peak fitting function. The differences are, in fact, I'll show you. We can reopen our builder and edit that function, my peak function, and go back through it. The main differences are we used Origin C. We defined it as a peak function. We said it was. And we had to choose these attributes. Those were the main one. For some reason, this one attribute did not stick, but that's okay. And also, we used Code Builder by clicking that button to compile and check that our function was proper. So those were the big differences between a peak function with Origin C and a regular function with an expression. By the way, you can have a regular fitting function with Origin C. It's a little more difficult, and it's considerably slower than using expressions. So let's go ahead and close. We didn't mean to edit our fitting function, so I'm just closing it, not saving changes. Now let's move back to curve fitting and look at a function with integration. And I do have a lot of notes on this. This is our function. We use integration in the fitting, and we have an integrand. And what we're going to do is we have to define a special function Origin uses to do the integrand calculation. It's going to use this function to integrate from -infinity to the current x value. The parameters used in the integrand include a w, an a, an x, and an xc. And we're integrating our integration variable is going to be t. So let's learn how we can use an integral in our fitting. Let me scroll on my notes a little bit. And let's open our builder. Tools, fitting function builder. We're creating a new function. Now, Origin, remember last time that I put my function in that PFW category. I don't want it in that category. This isn't a peak function. I'm going to come back and choose user defined. And I'm going to name this my int fit function. Again, explicit model. We're going to use an expression, but we need to check include integration during fitting. Now I'll click the next button, and we have to define our integrand, a function for our integrand. This is our integrand. What we're doing is we're creating a function here that Origin is going to call. Perhaps this is better named integrand function name. I'm just going to call it my integrand. We need our integration variable, if we look back at our function here, is t. So we're going to just call it t here. And we need arguments. The arguments are going to be essentially, for every parameter in our integrand, we're going to have an argument in this page. And we're going to prepend the letter I to our argument. So we have an IA. We have an IW, and we have an IXC. You'll remember that A, W, and XC pattern from the other functions I've done. Now, I'm going to minimize. I'm going to roll up my dialog again because I want to just copy this function. and I'm going to copy it. This is my integral function. It has to have what's called a return statement. It has to return something. I am not going to go through this particular function to describe it, but essentially it is a reworking of the integrand here into code terms. By the way, some of this is sort of complicated. I understand that. If after today you decide to start creating your own fitting functions, feel free to contact us in tech support. If you run into problems, don't hesitate to contact us. We deal with customers who have very, very complex fitting function requirements. They can be very difficult, and they can be difficult even for us, but we generally take the time to work out the fitting function for you. So don't hesitate to ask for our help in this area. Okay, so we've defined this integrand function called myIntegrand, and I'll show you how we're going to use that by clicking the next button. Now we have to define the actual variables we're going to use for the fitting. Independent is always X, dependent is always Y. Our parameters are going to be Y0. That parameter is not in the integrand. We have the A. We have XC, and we have W. Let's do W and then XC. No derived parameters or constants. It is not a peak function. And now for the trick part. Our function body is going to call that integrand function. And let me just copy that. So I'm going to paste my function body. Notice I didn't put a y equals because with expressions, there's already a y equals there. The way we're going to work that integrand is we pass that information to a LabTalk function called integral. And it accepts certain values. You pass it the name of the function you defined. You pass it the lower limit, which is going to be minus infinity. INF is a reserved word in Origin, meaning infinity. So we're going to have minus infinity. We're integrating to the upper limit is X, and we need to pass our additional parameters to the function. Now we have to come up here and define our lower limits. If you'll give me a minute, I'm going to scroll down. We have some tabs up here, the first being the integrand tab. So we need to set our lower limit. That's going to be minus INF, as I said. The upper limit, as I said, is going to be X. The IA value, it's the integral A value, is just going to be A. So we're going to pass A into the function. The IW value is just going to be W. And the XC is just going to be XC. We need to switch to a constants tab. We don't have any. In our parameters tab, I'm just going to give it some initial values here. I happen to know based on experience. 0, 0, 2, 3. Now you could do some code if you were brave. You could do some code to do some auto calculation here. That could be rather complex to figure out. So I just gave it some sensible parameters, and we'll do our check, our quick check, and we get a value. We'll go through our next. We're not going to use these codes to define our parameters. We don't need bounds or constraints or derived parameters or scripts, so we're done. We have defined an integral fitting function. Now let's go ahead and fit this data. Analysis, fitting, nonlinear curve fit, and I will open the dialog. Again, we're going to go to our user-defined category. We're going to find our fit function, my integral fit function. It's taking a moment. Okay. Let's see what happens when we fit it. I don't know what's going on here. We may need to check this. Oh, it just took a moment. Origin just took a moment to think. We seem to be having some issues here. Okay. It just took a little bit of a delay, but we can see we got a good fit. Let's look at our messages. We got a good R square COD. I think it had to do some compiling in the background. That's what it was. And we got a nice fit. So we fit that with an integral. We'll go ahead and fit it again. And we got that good fit. We're going to say OK. So that's how you create an integral function. Origin is calculating statistics in the background. That is how you include integration. You define that integrand function, you give it a return statement with your calculation, and then you're going to pass the parameters to it. All right, we're going to look at one more subject and we're going to take a break and do that poll. Sharing fitting functions. All right, so we've defined these fitting functions, but where is this information stored? It's actually stored in our user files folder in a specific folder. So let's go there. From the help menu, I can go to the user files folder. Help, open folder, user files folder. And here's my origin user files folder. If you're an advanced user, you're probably familiar with this. If you're not, this is where Origin stores a lot of files that it needs. Like we're going to see our themes or our INI files, things like that are in this folder. So are the fit functions we define. And if we're looking for this fit function folder, inside that we see a file for each fit function we've defined. It is an FDF file. I'm guessing, educated guess, that means fitting definition file. So these FDF files live in this folder. Now, what if I want to share this file with somebody else so they can use my fitting function too? All I have to do is get this file from this folder. I don't want to take it out of my folder. I'm going to copy it. I'm going to copy it and maybe email it or put it out on Dropbox or something like that. And later, let me show you how easy it is for the user to install this file. I've got off screen. I've got to actually have a fitting function. I just call it my function. Let's say someone sent this to me and I want to install it and use it in Origin. All I have to do, let me rearrange the screen a little bit, is drag and drop it into Origin. Origin will give me a couple prompts. Do I want to copy it to that default folder, that fit function folder? Yes, I do. I don't want to keep it where it is. Sometimes it will ask you if the original category for that fitting function was not user defined, it may prompt you whether you want to put it in a different folder than user defined. If it came from a user defined folder, it's going to go into the user defined folder, and there's my FDF file. And if I go to my organizer, tools, organizer, and I go to the user defined category, I can see it there. All right, we're going to take a break for a couple minutes now. We would like you to go ahead and fill in the poll that my colleague is setting up. Okay, let's look at some final subjects while you're finishing up the poll. They aren't specifically related to defining user-defined fitting functions, so we would rather you do your polling, answer the polls, but I will show these to you in the background. We have an app in Origin. It's called the Fitting Function Library, and let me install it. I'll go to my Add Apps icon, and I'm going to search for it when that dialog comes up. Fitting function library. And I will install the app. This is a pretty neat app. We already have over 100, we have probably nearly 200 fitting functions in Origin now. But this is an app that lets us add even more fitting functions or have them at our fingertips. These are mostly user-defined fitting functions or fitting functions users have requested of us that is not proprietary, it's not their own intellectual property, and therefore we may find these useful for other people. So with their permission, we uploaded these FDF files to our website, and you could download them if you need them. Each item on the list has the name and what it is, the model, and the equation. We can look at the first one. Can you imagine if we had taken the time today to do this one? This one is above my pay grade, frankly. You can request a new function from here. If you have an FDF you created and you think it's useful for other people, you can share it from here. You can even add functions from here. Let's add that convolution one. And I'll close the dialog. And when we go to our fitting function organizer, we can see that it got added. So that's that app. And we have a few more apps. We're out of time now. Well, we've got a few more minutes. Let me show you these apps. We have a Piecewise Fitting app. One of the more popular user-defined fitting functions that people ask us for is a piecewise fitting. And we used to show you how to create your FDF, your user-defined fitting function for a piecewise fitting. Instead, now we have an app, and we can install that too. Add app, piecewise fitting. Install it. Launch it. We're going to fit this real quick. We have a linear part and an exponential decay part. It's as simple as how many segments? We have 2. What is the X value at the intersection? And the app is smart. It goes through and it says, oh, it's about 5. So it starts at about 5. Then the function for the first segment, we're going to use an existing function. This is a nonlinear curve fitting function. Our linear function is under polynomial then. So it's a polynomial line. Our second function is an exponential decay. I'm speeding up a little bit here. I'm sorry. It's a one-term exponential decay. And we can do a fit. And say okay. So that's sort of the improved way of doing a piecewise fit now in Origin. And we have a result here. Actually, there should have been a report, but I didn't click the right button. I apologize. A couple more items. We have a Fit Convolution app too. This is mainly for signal processing. I've got a quote here about them. We had a tutorial about how to do fitting with convolution. It used to be if you had a signal that was convoluted with an impulse response, that you would have to deconvolute them both and then handle it. But this app does this work for us. As long as we have an X, a Y signal, and a Y impulse response, we can see how this app will behave. Let me add that. If I could spell it. Fit Convolution. So I download it and install it. Close my App Center. The app is going to look for a worksheet with this pattern, X value, sampling, signal, and impulse response. I just need to give it a function, and I forgot to copy the function. It's a simple exponential decay. In fact, let's just take a quick look at the signal. It's an exponential decay with convoluted. So let's reopen the app. I just have to put an exponential decay function here. And let's see what happens when we do a fitting. we can see that Origin fit it with a convolution. Report, generate a report. Yes, switch to the report sheet. And here we have a report. Last but not least, and I'm not going to do this one because it's very complex, we have an ordinary differential equation fitting app. This makes it a bit easier to fit with an ODE. Let's just look at the page. I'm sorry, I had to communicate with a colleague. I apologize. Rather than, let me find this fit ODE. Is that not what it's called? Let's just search for ODE. Here we have it. Rather than installing the app, I will take us to the file exchange page for the app, and we'll look at the dialog. It gives us a lot of control over the equations, the order, etc., etc. We have in this project that I'm working on that you will receive, I have a link to that file exchange page and a link to a video showing you how to use that app. So we're going to begin to wrap it up now. Our polling time is running out. I appreciate that you took the time to fill in the polling questions. I will hang out for a couple minutes if anybody has any additional questions. I appreciate you spending time with us today. And remember, we do have other webinars. Let me bring up that page for you. Upcoming webinars. Later this afternoon at 2 o'clock, we have a preview of the Python improvements in upcoming Origin 2021. There's some really great stuff there. At 4 o'clock, we have accessing databases. It's a great subject. If you have to work with databases, you want to watch this webinar. Next week, we have a basic statistics and advanced statistics webinar. And the week after that, we're going to have 2 weeks after that, we're going to have 2 more webinars. I appreciate you attending today, and I'm going to go ahead and sign off if that's all right. Let's see if all our QA is handled. Yes, it is. So I'm going to sign off. Thank you for attending.